All right, section 3.5 ellipses, first video that's actually on this worksheet. I just did a video talking about what conic sections are. Now we're jumping into ellipses. So ellipses are one of two conic sections we're going to cover this semester. And they look like this. They look like ovals. You could really just replace the word ellipse with oval, but mathematically we call these ellipses. The formula of an ellipse you might notice as similar to another formula you've seen. I don't know, something that looked like this: x minus h quantity squared plus y minus k quantity squared is equal to r squared. You may recognize as the equation of a circle. So this right here is the equation of a circle where the center of the circle is at h comma k and the radius is r. That's a circle. Circle. And if you look, these formulas down here look awfully similar to that circle formula. And ellipses in general are very similar to circles. So it makes sense these formulas are similar. The differences you're going to see is that the h and the y terms are being divided by an a squared or a b squared. And on the right-hand side, there is a 1, not an r squared. The idea of a radius doesn't quite exist in an ellipse because if we look at an ellipse, the distance between the center and the ellipse is going to vary depending on what part of the ellipse you're looking at. So the formula looks a bit different. The first thing you need to know is these A and B terms down here. They're the things that switch between these two versions of an ellipse. The way that we define ellipses, and I want to be very clear that this is for ellipses because hyperbolas have their own set of rules for A and B. With ellipses, we say that A is always the bigger number. That's how we define it. We say A is always the bigger number. Always the bigger number. So if the bigger number is under the x term, so a squared is going to be bigger than b squared, right? So if the bigger number is under the x term, that means that you have an ellipse that is wider than it is tall. Wider than it is tall. And if the bigger number is under the y variable, you have something of an ellipse that's going to be taller than it is wide. The axis that it is widest on is what we call the major axis. So this guy right here, his major axis, that's to do that. Major axis is the horizontal axis, the x. We're going to call it the x-axis for ease here. This is the major axis equals the x-axis. For this ellipse, I just made the hyperbola worksheet, so my brain is thinking hyperbolas. The major axis for a up and down ellipse, a tall ellipse, if you will, is the y-axis. Major axis equals the y-axis. For each of these, there's also that other axis that I don't have highlighted there. And if it's not major, what would it be? Good. You have a good guess, I'm certain. Just seeing the word major, the opposite, minor. There's a minor axis and a major axis. So the minor axis is going to be the smaller axis. This guy is going to be the y-axis. The minor axis on a wide ellipse is the y-axis. And the minor axis on the tall ellipse is the x-axis. And it's not necessarily on the x-axis, right? This could be the XY plane right here. I took the XY plane out of these pictures because I wanted to be able to zoom in far. Also, I made each of these pictures by myself using PowerPoint and Desmos. I feel very proud of it. You feel free to send me emails complimenting my beautiful graphic skills. I worked very hard on these worksheets. Hours on a Saturday. Anyway. So these exist in the XY plane. Their center is at the point H comma K. I don't have the XY plane drawn on there, but they do exist on the XY plane. Even though we're saying the major axis is the x-axis, it's not that the x-axis necessarily runs through here. It's not necessarily centered at the origin. It's better probably to say it has a horizontal major axis, but just take it for what it is. All right, so when the bigger number's under x, you end up with a wider ellipse. And if the bigger number is under y, you end up with the tall ellipse. You'll notice that there's some points plotted here. So I'm going to zoom in on this guy here. There are a few points plotted. They're on either side of the major axis. You'll see vertices. That's the plural of vertex. One of them is a vertex. Two of them are vertices. These right here mark the widest parts of the ellipse. So they mark the wide parts of the ellipse. The distance from the vertex to the center is A. We call that A. So the distance from the vertex to the center is A. Marking the shortest sides of the ellipse, the shortest radius almost, if you will, is the co-vertices. Each of them are a co-vertex. Together, they're co-vertices. The distance from the center to the co-vertex is distance B. Finally, there's this last very silly idea, and let me just kind of move this so I can explain what a focus is. The focuses are super, super special points. It's really silly what they are, very silly what they are, but they're super special points that are just so that if you take and plot any point on the ellipse that you want, and draw from one focus to that point, and then boop, like this. So each focus goes to that point. If you were to add up the lengths of this guy here and this guy here, they are the same no matter where you put that around the circle. So hold on, let me see if I can do this with it paused. All right, let's see if I have a good example here. So I took this guy, these two lengths here, and then I went ahead and did another one, right? Any point on the ellipse, you can take these two sides here. And sorry there, noise in the house. So anyways, we take these two sides here, and we did another one down here. It doesn't matter where on the ellipse you are taking those two lengths from, but I took them and I copied and pasted them down here. And you can see, so all I've done with these is I copy and pasted them, and I just kind of like, made them connect together. You can see that the green and the black and the orange and the red are the same length, more or less, because, I'm precision, but those two lengths are the same. So it's that same anywhere, any point you pick on the circle, those are what the foci are. Oop. Well, you know what? I'll leave that page in because it's fun. All right. Good enough. So, boop, boop, boop. Move him back. Where were we? Those are what the foci are. That is where the foci are. The distance between the center and each of the foci is the distance C. So the distance between the center and the co-vertex is B, vertex in the center is A, center and the foci, that's going to be C. The center itself is at the point H comma K. So for a wide ellipse, the major axis contains, well, for all ellipses, the major axis contains the vertices and the foci. So the center is on the same y level. They just have different x values for the vertex, the two vertices in the center. This point right here, for the wide ellipse, it has the same y value as the center because it's on a vertical level with it. But instead of h for its x value, it's a units backwards, which is h minus a for this point here. On the other hand, this point here, the x value is going to be h plus a, and then the y value stays the same. You'll notice that these are, boop, those formulas right there. That's why it's plus or minus. There's one on either side. For the co-vertices, this guy has the same x value as the center, so it has h as the x value, but then it's b units up from the center on the y direction. So it's the center is h comma k. If we add b to the y value, then we're up at the co-vertex. For this down here, h comma k minus b. Finally, these foci. This guy right over here, he has the x value, h minus c, because this distance right here is c. Same y value. Over here, this is h plus c, same y value as the center. On this guy over here, the vertex up top, it has the same x value as the center, so the x value remains the same here. It's h, but the y value has a added to it, goes up a units, so it's k plus a. On the bottom here, same x value, h, but k minus a, because it is a units down from the center. For the co-vertices, these have different x values. So this is h minus b. The y value is the same. This guy over here is h plus b. The y value is the same. For the foci, this is going to have the same x value, so h, and then it will be k plus c. Down here, this is going to be h comma k minus c. So all of those are given up here. It's just, nice to have them labeled as well. The other formula that's given on here is 2a and 2b for the lengths of the major and then the minor axis. This makes a lot of sense here. So if we say that this distance is b and this distance is b, the length of this entire thing would be 2b, long. It's the same idea for the minor, sorry, that's the minor axis. For the major, for the major axis, it's a. So if we come here, this distance is a, this distance here is a. So the distance across the whole major axis would be 2a. And that's that formula you see there. It's the same for the tall ellipse, 2a and 2b, those are the formulas. On a test, you will be given, this amount of information. You'll be given this amount of information, and you'll also be given some formulas down here. Almost everything on this page, except for not this information, that will not be given to you on your formula sheet. Nor will this particular line that a is always the bigger number. This will be given to you. So if you can read this, this says a should be bigger than b, which should be bigger than 0, i.e. they're both positive and a is bigger than b. This formula is down here. C squared is equal to a squared minus b squared. That's how we get the distance c that works perfectly so that these foci are, such that these distances add up to the same amount no matter where on the circle you do it. This can be rewritten in 3 different ways for 3 different formulas, depending on what you need it for. So, boop, there you go. A reminder, A is the distance from the center to the vertices, B is a distance from the center to the co-vertices, and C is the distance from the center to the foci. The variable with the larger number under it is the major axis, and the vertices and foci are always on the major axis. So they're always together on the major axis. That is true of both ellipses and hyperbolas. Okay. Scroll down a bit. So a quick review of all of it, and you can see it just real explicitly here. For the wide ellipse, you can see, poop, this distance is a, this distance is a. And then thusly, it makes sense that this entire distance here is 2a, the length of that axis, right? And if you look here, right, the length of the major axis, 2a. For the covertices, they exist on the minor axis, and the distance from the center to the covertices, is b, which means the length of the entire minor axis is 2b. Same idea over here. The length of this entire thing is 2b. And then for the foci, c is the distance from the center to the foci. Boop, c. The formulas are all given down here. So our next video, we'll actually get into graphing those, but that is the setup. That's everything you need to know about the formula, the standard form of an ellipse. See you in the next video, and we'll talk about graphing ellipses in standard form. Bye.